Oh, this thing's on? Okay. Good evening. Welcome to another video. Another boring, corny video. It doesn't matter. All right. This video is going to be on factoring. Factoring, probably in my opinion, is one of the most important things to learn in mathematics because it's used in all the other kind of mathematics like pre-calc and calculus and all that other good stuff. You'll see factoring a lot more than you'll probably see anything else. So we can just get into it. All right, there's three types of factoring: common factors, difference of perfect squares, and quadratics. Now, there are derivatives of these with the factor, with common factor, difference of perfect. You'll see other forms, but for the most part, these are the main ideas. What you'll be happy to know is today we will not worry about quadratics. So let's just X that out. All we'll worry about is common factors and difference of perfect squares, and and the ones that are like it. But those are the ideas. All right, so let's move forward. Common factors. Now, common factors is just exactly what it is: factors that two terms would have in common, or three terms, or four terms, just whatever they'd have in common. Simple example. What do these two terms have in common? And if you break it up, it's very simple to see. This is 2 times x right here. And you break this up, this is 2 times 2. So obviously looking at them, they have 2 in common, right? So since they have 2 in common, that's the greatest common factor. So what if in fact this was a binomial? So 2x plus 4. And your directions on this was very, very simple. Your directions on this was just factor. So with this 2x plus 4, the thing is, what you want to do is you want to, take your common factor or your greatest common factor and take it out of the parentheses to be by itself. So the way that we'll actually do that is notice that here you can actually rewrite this, and 2 is going to be your common factor in there, isn't it? Because you're going to have a 2 times x plus 2 times, wait a minute, 2 times x plus 2 times 2, right? Inside. So you agree that we'll go from here to here. So since they both have a 2 in common, we take that out of the parentheses. Kind of like a reverse distributive property, right? So if in fact we take that 2 out of the parentheses, wait a minute, let me be consistent here. If we take the 2 out of the parentheses, we are left inside with x plus 2. And the reason why we know this, if in fact we distributed this 2 back in, wouldn't we just end up with this again? So that's the whole idea behind common factors. That's the small idea. Of course it gets way more difficult than this, but that's the broad idea behind it. So let's do some more difficult ones just to get a better idea, I guess. Let's talk about, say, let's do 3. I don't want to do 3. Instead, let's do 6x cubed plus 15x squared. And we're doing common factors, right? So it's you have to take a factor that they have in common. Looking at these, what do you think they have in common? Now, doing more and more of these, you get better and better at them. So we can look at this and we can tell that between 6 and 15, the common factor between 6 and 15 is going to be 3. All right? So, and the common factor between x cubed and x squared is going to be x squared. So 3x squared is a common factor between the two, right? And you have to, so that means we're multiplying this 3x squared by 2x, right, to get 6x cubed. And we're multiplying 3x squared by 5 to get 15x squared, right? So the actual problem can break up to be 3x squared times 2x plus 3x squared times 5, right? And then what we do is we draw that 3x squared out, don't we? So if in fact we draw that 3x squared out, we'll end up with what's left in black, which is the 2x squared plus 5. So that's the idea behind common factors. If we keep on going, let's move on. And let's talk about difference of perfect squares. Now, there's this really cool thing that I can show you with odd numbers and difference of perfect squares, but for the sake of time, let's just keep on moving. Now, with difference of two squares, now what I mean by a perfect square, I'm talking about things where you take a square root of a number and you'll get an integer. So we're talking about numbers like 25, 16, 9, stuff like that. Notice what happens if I take 25 minus 9. What you'll see from here is that you'll get 25 plus 9 times 25 minus, well, actually, you know what? Those numbers are a little bit too big to even see it. Better way to see it. If we do 9 minus 4. Now, doing 9 minus 4, notice that they're both perfect squares, right? What you'll see with these right here is you'll see that if you do 3 plus 2 and 3 minus 2, multiply those two things together, you're going to get what 9 minus 4 is. So that's just ideally 9 minus 4 is just going to give you 5, right? 3 plus 2 is 5 times 1 is going to give you 5 as well. There's a whole bunch of good things to do with that. But from here, we can actually conclude that a squared minus b squared equals a plus b, a minus b, all the time. So from here, all you got to do is just really substitute. Whatever a squared is, whatever b squared. It does get complicated, but showing you the basic idea. This example, I'll even put example so we know. Say y squared minus 9. Do we agree that they're both perfect squares? Yes, they have to both be perfect squares. That's why you see a squared and b squared. Notice here in this problem, I use perfect squares. It doesn't really work all the time if in fact it's not a perfect square. If it is a perfect square, it's going to work all the time, every day, and twice on Sunday. So from here, all we're doing is substituting. We understand a squared is y squared, b squared is 9, so we just substitute right across. If a squared is y, then that means a would be, if a squared is y squared, then a would be just y, wouldn't it? So you have a y here, and since b squared is equal to 9, b would just be 3, wouldn't it? So this would just be y plus 3 times y minus 3. And if in fact you FOIL this back, guess what you're going to get? You're going to get this. I'll give you another example. However, they do get complicated. So let's say I do something like 4x squared minus, let's say 9y squared. Let's make it simple for now. 4x squared minus 9, and let's chop that up. So now here, do we agree that this is a perfect square? Yes, because the coefficient is a perfect square and the variable is a perfect square. So 4 is a perfect square and x squared is a perfect square. So we can do that, and 9 is also a perfect square. So since that's the case, what are we going to end up with? What number can I multiply by itself to get 4x squared? And that would be 2x, wouldn't it? So you'll get 2x plus, not 9, but 2x plus 3, 2x minus 3. Fair enough? All right, so that's the idea behind difference of perfect squares. Difference of perfect squares is actually the easier one to do because it's no work is necessary. You just recognize the perfect square and you just do what you need to do. Next one. You have difference of perfect squares. The derivation of difference of perfect squares is the sum and difference of perfect cubes. Now, with the sum and difference of perfect cubes, there's two things that you have to remember. You're going to have to remember. Now, perfect cubes, just to let you know, perfect cubes are numbers that you can multiply by itself 3 times, and it will give you another number. So that's what a perfect cube is. For example, 1 is a perfect cube. Why? Because 1 times 1 times 1 is 1. 8 is also another perfect cube because you can multiply 2 times 2 times 2, and that gives you 8, right? So if you took the cube root of these numbers, you'll get a whole number. Another perfect cube would be 27, wouldn't it? Because that's 3 times 3 times 3. So that's the idea behind perfect cubes. Just so you guys can see a visual of what I'm talking about. And that's about as far as I'll go with that. Now, with perfect cubes, let's talk about the sum first. So if we're talking about the sum, we're talking about something that looks like a cubed plus b cubed. It's the sum of perfect cubes, right? So cubes are going to be in the form of a cubed and b cubed. Now, since we got that part, when you expand, that expands out to look like this. We're going to say a plus b times a squared minus 2. Well, not minus 2. I'm sorry. I was thinking of something else. Minus ab plus b squared. So that's going to be for this one. And for the difference, so we're talking about the difference of perfect cubes. That's a cubed minus b cubed. And that's going to equal a minus b times a squared plus ab plus b squared. So for the most part, all you're doing is substituting. Just substitute. Just substitute. Oh, this is not writing anymore. Oh, man. Sorry about that. I had to get my pen working again. So really just substitute and you will be fine. I'll give you a small example of this. If you're trying to do this, let's talk about y cubed minus 1. And just like that, it's fixed. Now, y cubed minus 1, all you have to see is how to actually break it up. The one that we're going to use, we're going to actually use the difference for this one, right? The difference of perfect cubes. So all we got to do is just follow exactly what's written there. So in this case, a cubed minus b cubed is a minus b. So that means the first part of this is going to be y minus 1. Well, we understand y cubed is a perfect cube and 1's a perfect cube. Times, now this is the one that can actually a little bit tricky, right? So a squared, so in this case right here, if we're substituting, we're talking about y squared times ab, ab meaning y times 1, which is just going to be y, plus b squared. And that's 1 squared, so plus 1. And guess what? You're done. So that's easy enough, right? So if we talk about other ones, it's pretty much the same thing. Let's do one that's a little bit trickier, and let's see how well we can do with it. Let's say 8 uv, well, 8u cubed. Let's do that. 8u cubed plus v cubed. If we do this one, we understand this is a perfect cube and this is a perfect cube right here. So if that's a perfect cube and that's a perfect cube, then we can go a little bit better from here. First off, we have to understand what a would be in this case right here. Now, since 8u cubed is a perfect cube, well, we have to multiply 3 times to actually get 8u cubed, and that will just be 2u, not 2y, 2u. Why? Because 2u cubed is going to be 8u cubed. I'm sorry, 2u. If you cubed 2u, you'd get 8u cubed. 2u plus v. Why? Because you have v cubed right here, right? So then you multiply again. This is going to be a squared. So remember, you're doing 2u squared, so you're doing 4u squared, right? Because in this case right here, it might benefit to write down what do you want for a and what do you want for b. In this case, a is going to be 2u, and in this case, b is going to be v, right? So then we have a squared, and this is going to be, where we at minus, I'm sorry, so we're going to get minus ab, which is 2uv, and then plus b squared. In this case, b is equal to v, so v squared. And guess what? You're done with that. So this is the idea behind sum and difference of perfect cubes. But we'll do more of these in the future just to really get a hang of those. Last thing, factoring by grouping. Now there are some parts of this chapter that I wanted to cut out and we'll do later. So we'll just end on factoring by grouping. In factoring by grouping, you're dealing with 4 terms. Any polynomial that you get that has 4 terms, you should look to group. And what I mean by that is you're going to group 2 together. So I'll show you exactly what I'm talking about. So say, for example, we have this term. And the thing is, you should look to group once again if, in fact, your polynomial looks weird. So say if your polynomial looks like this. Now, mind you, that's a weird polynomial. Ideally, you want to group like terms together, or terms that have something in common together, just to help you out. So for the most part, just move some things around. I'll just put move things. All right. So if in fact you're moving things around, it might look a little bit better. So what if I grouped this together with this, and I grouped this together with this? Notice what they have in common, right? Notice that the 3xy and the 6x have a 3x in common, and the 2y and the 4 have a 2 in common. So if I group it together, then I can rewrite it to look a little bit like this. 3xy minus 6x. Oh, also carry the sign with it. Since there's a minus sign in front of the 6x, I'm going to carry that minus sign with it. Plus 2y minus 4. Now it looks a little better, not totally, but it looks a little better now. It's now no longer that weird. So in this case right here, what we want to do is we want to group them together like that. Group them together with some parentheses. And then it starts showing it in a little bit better perspective. A little bit better perspective meaning 3xy minus 6x will be over here in parentheses plus 2y minus 4, right? So those two things will be in parentheses. And now, when you look at it, you can perform a certain type of factoring with that. What type of factoring can you actually perform? Common factors. Here you have a 3x in common, right? So you take a 3x out of here. If you take a 3x out, what do you have left over? With this case, you have a y left over. In this case right here, if you took a 3x out, you're just going to have a 2 left, right? Now here, you take a 2 out, right? This has a 2 and this has a 2 inside of it. So once you take a 2 out, what do you have left inside? You have a y minus 2. Now, the work is not done. You did common factors, but guess what? You also have something else in common. What do these two terms have in common? And if you look carefully, they both have a y minus 2. So since they both have a y minus 2, it's hard to see it, but you can factor that out. So if I factor out y minus 2, if in fact this was a huge parentheses right here, and I took y minus 2 out of my parentheses, what's left inside? You have a 3x plus 2. Makes a little bit of sense. If you want to do another one like that, just raise your hand. Okay, I see somebody's hands raised. No, I don't. I don't see any of these hands raised. All right, fine. Well, I'm actually going to cheat. I said that I was going to limit it to 5 pages. And I'm actually going to go. Actually, we're going longer than I thought we would. So I'll just cancel the video out right there. All right.